All right. So we're going to do some worked problems from chapter 14. And I'm just looking at the list of problems. I'm going to just see what 20 and a half is. That's the first one of the bold ones that I see in there. So I'm going to look at 20 and a half. I guess it's not the first of the bold ones, but we did something very similar to problems 2 and 4 in the lecture the other day. So I want to try some gnarly buoyant force problem, which I think is 20 and a half. Okay. Oh, you all right?
Oh, sorry, I'm unmuted.
Oh, well, it's only on the live stream. I'll try to figure out how to edit that out. All right.
That was my bad.
No, it's all right. I do it all the time too. It's like I can't help it. It's a bad habit. All right. I think you were talking about ducks. That's what I heard. So in this case, on page 137, we have an aluminum pipe. And do I have it up here? You guys have it in front of you. I'm going to screen share it just in case people need that. Screen share. Where did it go? There's this one. So I think we said 20 and a half. There. Oh, I passed it. Okay, so we're looking at this one. An aluminum pipe with this height, this density, all these properties. The pipe is suspended from a light spring halfway submerged in a fluid of density, blah, blah, blah. The spring is stretched distance y. Okay, so it's stretched some distance, not compressed. Determine an algebraic expression for the spring constant. Woof. Looks crazy, right? Any ideas what we might do to get this started? You think about it while I get the picture drawn up, okay? So I can do it on the whiteboard. Okay. That would be a neat feature if they could figure it out. Auto censor, like if it could detect the Zoom live stream and censor me, that would be cool. Oh, well. Having willpower and self-control would probably be even better. Any ideas how we might approach this while I'm drawing it up here?
I think I have an idea.
Okay, kind of tell me what you're thinking there.
We could probably do this like chapter 8 style, like energy.
That is not a good idea, it turns out. That's one of the two things I would expect you to think of. And it turns out that's the bad area to go. In this case, there's a key word in the problem that tells you it's not going to be a chapter 8 problem. What's the special keyword in this problem that helps you identify it's a force problem?
Is it equilibrium?
Equilibrium. Doesn't that mean force is balanced? So the word force is hidden in, you see what I'm saying?
So this is actually chapter 12, kind of, too.
Yeah, it's a statics problem or it's a force problem, no matter what, okay? So what we've got here is it's some kind of force problem. And sorry, this is so sloppy. I'm going to redo it. It's not very pretty, but you get the idea, right? So we know the inner radius is 2/3 of r. The outer radius is r. I know the height is h. Is that right? Oh, yeah, the height is h. We know it's aluminum. So I'm kind of listing out all of my givens here, all of our known quantities. It's 2/3 submerged or something? No. Oh, the spring is stretch distance Y. We know it's in equilibrium. Geez, there's a lot of stuff you have to read and interpret here, right? You've got to read all these and say, these are known quantities. I know that the word equilibrium was used. So that tells me force is balance. That's what cues me in to do a force problem. That's what equilibrium means. And we know it's halfway submerged. That's another piece of information. That is a lot of stuff. That's what I get out of reading the problem. Is that okay or not?
Yeah.
I claim that all of these givens matter. There's no decoy information in this problem. Okay. What should we do from here? Anybody?
FBD?
Correct. Forces, FBD, worth a shot. Well, Jesse, you made the mistake of speaking up. What's one force?
There's going to be an mg pointing down, of course.
Okay. You want to do another one or not?
Yeah. Then would it be tension up?
What attention is usually associated with the string. This is a spring.
So a K up.
K.
Ooh,
X.
X, yeah.
Anything else?
Is it touching at the bottom? No.
Nope.
I think that's it. Oh, nope. Buoyant force.
Exactly. Because even though I didn't draw this here, we're assuming it's halfway submerged, right?
Correct.
So in this case, there's a buoyant force up. Now, I don't know which is bigger, the spring force or the buoyant force, right? It depends on the spring and the fluid and the densities and the volumes, whatever. Okay, now let me read this carefully here. Okay, it's a pipe. Got it. Okay, so now what would you do? Let's pass it off. Jesse contributed there. Gonzalo's contributed here. Somebody else want to give it a shot? What might we do next?
Sum of forces equation.
Yeah, so what would that be?
Kx plus b minus mg
Okay.
equals 0. So, static.
Yeah, because it's in equilibrium. That tells us acceleration is 0, right? So then the ups equal downs. Nice job. What are we supposed to solve for?
K.
K. So shouldn't that be just, let's see, minus b divided by x, I think. Help me if I screwed it up and going too quickly.
That looks right to me.
Is that good enough for the final answer?
It says in terms of the givens in G, but we don't know B. So
we don't know B and we don't know M. Or do we know M?
Oh, wait, no, we don't know M.
So this is most of the battle. The last part is rewrite the unknowns M and B in terms of the givens. But this is the bulk of this question. So let's pause here and make sure that's good with everybody. Okay. All right. Who's feeling brave? How could I get the mass? What's the trick for a lot of chapter 14 problems There's a standard trick we use in chapter 14. Mass relates to what other property that was a given?
Density.
Density. Okay, how does mass relate to density? Give me any equation that has mass and density in it in any form.
B is equal to density final times the volume of the displacement G.
Careful, careful. That's not right. Density of the fluid. F in that case means density of the fluid. Wait,
Oh,
so
I
you're
thought that was
talking.
final.
Nope. So buoyant force is density of the fluid. Now we see the advantage of coding and using good variable names rather than just subscript F saying the word fluid. Probably would have been smarter in my workbook, but nobody does that ever. So I'm a bad person. Times volume displaced times G. That's one equation. Do I know the volume displaced? Do we know the fluid? Oh, we know rho of the fluid as well, right? That's a given. So how do I get volume displaced?
The length times height, pi r squared.
Say again.
Would be pi r squared times h. Yeah, length times.
I tell you what, let's come back to that. You're on the right track. How do I get the mass of this object?
Density times the area.
Density times what?
The area? No, the volume.
The volume of the object. What density should I use?
Aluminum.
Aluminum. I probably should have written that in black, but I didn't. Now, what's the volume of the object? And then, so Dena, the reason I called you off there was, do you agree the volume displaced is half of the volume of the object in this case? So that's why I was like, let's just get the volume of the object first, and then we'll just divide it by 2 for this. Is everybody okay why I do that? Half
Yeah.
of it's submerged. So I take, okay, got it. All right,
Oh,
go
you're
ahead.
solving for the mass of the aluminum pipe.
Do you agree the mass is not known? So I write down an equation that relates to the mass, right? We know that density is mass over volume, kilograms per meter cubed. Use the units to check it, or it's on the back of your equation sheet, on the back of your book. So you rearrange that for this. And so the idea is, I don't know mass, but I do know the density, and I think you could tell me the volume from that crap that was given. Does that make sense where we're going with this, Gonzalo?
Yeah.
Yeah. So we're taking something that's unknown, incorporating one of the knowns, and then like, oh, I got it. All right. So how do I get the volume of the object? Dena, let's go back to you.
The height times it's a sphere, so is that pi r?
It's a cylinder.
A cylinder, the 2 pi r times
Okay.
area.
Let's just go back to a cylinder. I don't know if this is showing up there. Whoops, there it is. So there's my cylinder. What are the main dimensions usually given to you for any cylinder?
Radius and height.
Okay, there's a radius and there's a height. How do you get the volume of a cylinder, right? We're trying to get the volume, not the perimeter. 2 pi r is the distance around.
Pi r squared.
Pi r squared
That's it.
times h.
Mhm.
Area of the base times the height.
Well, would that work because we have 2 radii?
Ah, so what would I have to do? Yes, I
Subtract
see
the
it
big
there.
radius from the small one, like Jake said.
See where I'm going with that? And that's probably what Jake said in there. So the idea is you just take the big volume minus the whole. That's the trick I've been trying to show you various times. Chapter 1, chapter 9, chapter 10, chapter 14. It's very useful to split things into parts. Here we have a positive part and a negative part. At this point, we know this, 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 so we can figure out mass. We've got it. And we furthermore know that the volume displaced equals 1/2 of the volume of the object because half of it is submerged. So we in theory know this. So we in theory know this. We've got it all done. Did I lose you or was that making some sense? Go ahead.
I had like a Jimmy Neutron moment. Like it all just kind of clicked right now.
Mm-hmm. I'm telling you, you're really close there. I mean, it seems like you're right on the precipice of having a good final. So, you just keep practicing, keep working. Maybe this is that time when it all comes together, right? That's what I'm hoping for you guys. Fingers crossed. All right. So, all that practice, it's like seeing it for that 50th time. Kind of like, oh yeah, I got it. All right. That's part A. Now to be, that's like the worst statement you could ever hear. However, as in all physics problems, usually part A is the worst, right? Because you're like, I have no clue what I'm doing. You spend forever on part A trying to figure it out. Then you start turning the crank. You're like, okay, I could see how to analyze this now. Let's go to part B. Let me see what it is. Oh. What if I use Flex Seal on the bottom of the pipe? What would be different if I had used Flex Seal?
Does it have the same density as aluminum?
It has a negligible volume and mass. So fortunately, we can ignore any contributions to mg.
Oh, I see it now.
Yep.
Wait, there's a hole at the bottom. I don't see it. Oh,
It's a pipe,
okay, never mind.
right? Dope pipes have basically a hole at the top and the bottom.
Okay, so that means like the water was coming
in.
Okay, so if you seal it, I think more water volume is going to be displaced.
Yes. Nice. How much more? How do we fit? So do you agree volume displaced? So in part B, if I could, part B, do you agree that volume displaced is no longer equal to half of the volume of the object? It's no longer equal to half the volume of aluminum that the pipe is made out of, right?
So the displacement is going to be double.
Is it?
I think so, because we're not subtracting from like big
wait,
radius.
you just said it. It's 1/2 of the volume of aluminum without the subtraction. That's what you just said. That's not necessarily double. It's exactly what you said the second time. It's 1/2 of the volume of the aluminum without the subtraction, without the whole. Pi r outer. That's the volume displaced. Do you agree?
Right.
It's 1/2 of the shit without the stuff erased or without the whole subtracted.
Okay, so that might not necessarily be doubled, but it's still going to be more.
It's probably
water
about
displaced.
double, but right. It's because the radius, remember that one of the radii is 2/3, right? So it's like, I have no clue what the number would be. And in fact, it's actually 9/5 bigger or something like that. Because right, 2/3 radius ends up being 4/9. So when you subtract the radius, you get 4/9 r squared. And so actually it's bigger by a factor of, oh wait, no, then you have to subtract it. You get an r squared minus this is the whole. So that ends up being something like 5/9. So yeah, I said it right the first time. So it's actually 9/5 larger which is almost 2, but not quite. You see what I'm saying?
Yeah.
Yeah, but you had the basic idea correct. It's about twice as much. Not quite. What do you think? And then, do you agree everything else is exactly the same up there? Oh, let me check the chat. Hey, this is flex tape. Yes. Oh, and then Jacob, yes, it's just like a solid cylinder for the displacement side, but not like a solid cylinder for the mass side. And that's what's tricky. So again, it would be the volume of the object is still the volume of aluminum present. So that's with the hole. The volume displaced is treat it like a solid cylinder with Flex Seal. What do you think?
Okay, so we can ignore the top part then.
Everything else is the same. This is still exactly the same. Oh, wasn't the spring stretch distance Y, not X? So I think this should be letter Y. I'm sorry. This should be letter Y, but yeah. Spring was stretch distance Y. So instead of KX, this is KY. So this is a Y on the denominator. Sorry about that. Okay. All right. Let's check part C. Now it says part C. How does the work from part A change if the spring is compressed instead of stretched?
The volume displaced would be less, wouldn't it?
Well, we're still going to assume everything else is the same, including this distance. So let's say it's compressed distance Y and it's still in equilibrium. I'm in class. Hold on. What's that? Yes, you can shut the door. Thanks. Sorry about that. Okay. Okay, so I'm assuming it's still basically the exact same picture, but let's say you're told the spring is compressed. It's still in equilibrium, but it's compressed distance Y. So I'm sorry, I think that was Jesse. What were you saying?
I was saying how the volume would be displaced, but it's going to be the same still. So
The volume displaced is still the same. Is anything different?
The arrow for the force for the
Aha. Oh, and there's the chat here. Oh, yeah. Yeah, there it is, Alonzo. Thank you. That's the main difference. If it's compressed, the spring does not push up, it pushes down. You could imagine, for example, imagine putting this on a test and you could have one version have compressed, one version have stretched, one version have hollow, one version have not, right? There's a lot of ways you could do this one. So, but at this point, I feel like you pretty much know anything you could, that's like all the variations you could do for springs, buoyant force, mg. I guess you could throw them at an angle or something, right? But all that does is add a sine or a cosine, right? You could put it so that it's touching the floor. If it was touching the floor, what would that add to this?
A normal force.
That's right. And then in the end, it's basic chapter 5 stuff, but we have this extra layer of figuring out B, which in these problems, the hard part is getting the volumes. Agreed? It's all about figuring out the volumes. And like Gonzalo pointed out at the beginning, keeping track of what the densities are. Okay, density of the object versus density of the fluid, and making sure you use the right one in the right spot. So subscripts are useful here. What do you think?
What helped me for number C was the word work. That kind of like told me this is gonna have to do with forces.
Yes.
Because
yeah. So Gonzalo, here's the trick that you mentioned earlier. You were thinking it was a chapter 8 problem because you saw a spring, right?
Yeah, and then I thought like, oh, maybe an energy equation would like fix everything, but no.
This rule I'm about to tell you does not always work, but for this class, it usually works. So I'm going to tell it to you just in case it helps you. If a spring is changing length in a problem, usually you have to do it with energy. If the spring is in equilibrium or at a set length, you would not do that. You would probably do forces, because springs and energy usually need an energy initial and an energy final. So usually the spring is changing. You know what I'm saying?
Yeah.
So keep an eye on that in a problem. If it says the spring is initially this and then it moves, now we have to be careful. Like I said, there's different ways to clue you into that. In this problem, I clued you in by saying the word equilibrium. Then you're supposed to go ding, 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 think about force. Now, obviously, in this problem, forces meant the forces balance. What if we did a problem with like a potential energy graph and I said the word equilibrium? Let's say I do a plot of U versus X. Do you know what I mean? What does equilibrium mean in that context? Because that was a chapter 8 problem. I'm not sure if you're talking or not, Jess.
It's like at the bottom, like where it can't like move, or like it's like at a dip.
Okay.
So it's
Or-
stable. It doesn't move.
That's a stable equilibrium.
Correct.
Stable equilibrium is at the bottom of a well.
Correct.
What's
yeah.
the key thing about all equilibrium points on a U versus X graph?
They don't change, I guess.
What doesn't change?
The energy. Or the U.
Okay, so yes, U is approximately constant over a small region, which says what about the slope?
Oh, it's 0.
Yes, zero slope is an equilibrium. So notice the word equilibrium in that context is very different than equilibrium in this context. So you kind of have to know that like there's a case where equilibrium actually implies it's a chapter 8 problem. And you're like, so I don't know if I'm making this better or worse, but yeah.
Worse.
Okay. Spring changing length, try energy. Spring at set length, try forces. How about that?
Yeah, better.
Okay. All right. Should we look at another problem here? Okay, so I'm just looking at my numbers here. 21. Ooh, this is a fun one. This is a good concept question. It's not one of the bolded ones. I'm going to let you read this at home, all right? Let's go to the next bolded one, which I see is 28. Oh, we did that one. All right. Let's go to 29. You guys want to try one of these? I think this is about right, because then we've done one more buoyant force, one more fluids in motion. That's a pretty good start. How about we try this one? Okay. These problems are surprisingly sneaky. So let's see. What should I
Wait.
do for? Oh, go ahead.
Are these the ones we went over in class earlier? Or
This is the ones we went over in class last time. Yes. Now, here's the deal. You're about to take a final exam. The final exam is no holds barred, any questions from the whole thing. So it's not like you could just look at it. When we look at this problem, you're probably thinking, well, I need to use Bernoulli's equation because this is a Bernoulli's equation problem. However, during the exam, that might not be so obvious. And in fact, with a lot of these problems, sometimes you have to use other chapter techniques. So sometimes you might want to use energy or kinematics, like the last problem. We discovered we needed kinematics. So, and maybe you need to use vectors or sines or cosines or something. So let's go through these parts. And before we do them, let's see if we can figure out what approach we should take before wasting time doing anything. It says, determine the desired speed at which water exits the nozzles. My givens are the height h, the diameter of each nozzle, blah, 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 blah. Okay. Got it. I know a bunch of distances. I basically know a bunch of distances, right? And diameters and stuff. How do you do part A? Any ideas? I'll give you a second to think. Any guesses?
Fluid in equals fluid out?
Nope. That's what you would think because of this chapter. Now, okay, you said fluid in equals fluid out. What is that equation?
A1 V1 equals A2 V2.
Okay, so I would write that down first, to be honest, because I see this, that's immediately what I think. What's the problem with this? Do we know the areas?
Yes.
Do I know V2?
No.
Do I know V1?
No.
So that's why that doesn't work.
Yeah.
All right, that's fine. So that was a good guess. We see that fails. Oh, let me check the chat here. Kinematics. Jake is right. Don't we know? What's the speed of the water when it hits max height?
0.
Oh.
We know delta. So you see what I'm saying? So this is 2 fluid problems in a row. So this is a good candidate for a final exam problem, just like the last one. Why is this one a good candidate? This one's nice because it's a way to talk about fluids and kinematics, and you can kill 2 concepts with 1 problem on the test, right? But, right, you have to see that a fluid flying through the air is a kinematics problem. And that's something we've seen twice now, once in lecture last time, once today. So here, the trick is don't overthink it, kinematics it. Nice job, Jake. And do you agree from there, what are we solving for?
The initial?
Yep. And I think we could get it because we know 1, 2, 3. Which equation would you use without writing them all down?
Probably V squared.
Yes, V squared is a great one to use at max height. That problem's done. Next, how do I determine the flow rate required in the mains?
Now we know V1, right? And we know A1.
So how do you get the rate?
Well, you just multiply them, right?
That's it. A1,
Okay,
V1.
yeah.
Once again, we see the challenge of a physics class. Everything's easy after part A. it's so hard on students doing this because you're not used to having to think a lot before getting the first part. You get frustrated, you get anxious, you bomb it, and then you're right, it snowballs out of control. All right, so we've got that. How do I get the fluid speed in the mains? What am I looking for? What is fluid speed in the mains?
The pipes.
Yeah, what is fluid speed?
The rate.
Nope.
Oh,
Flow rate and fluid speed are different things.
that's just V.
Yeah, so I'm looking for V2. How do I get that?
Isn't that just the same as V1?
Nope.
No.
Is it A1 V1 over V?
That's Jesse's continuity equation. Now we know this, and this, where we didn't know it earlier, right? We didn't have V1 earlier. Now that we know V1, Jesse, are you good with that?
Yeah, I see it now.
All right. Do you think it is reasonable to consider fluid in the mains as being at rest relative to them? What do you think?
No.
Why not?
I mean, it's still moving, right? Like,
It's all pressurized. It's like all like. There's
What was the
no-
shortcut I told you? Do you remember?
oh,
Remember that? I briefly mentioned this. I said anytime the larger diameter is about 3 or 4 times the diameter of the hole, then it's negligible. Is that appropriate in this case?
Yes, because it's 10 times larger.
No,
Oh,
because there's 5. Right? So you effectively have 5 times little d squared, not just d squared, right? So it's, I don't know, it's close. The total area is 5 times this, whereas the big area is, okay, I'm not sure. What we could do is we could run the numbers here and look at the math, because these ones we'd have numbers for, right? Let's go look at the numbers. Oops. My guess is, I don't know. That's my guess, is I don't know. I don't think so, but Jesse, do you agree there's 5 holes, not just one now?
yeah.
So here it is. As long as that's the one I was talking about. Oh, okay. So let's see. One of these speeds is 7.6. Actually, I don't know. It's probably about negligible, to be honest. So V1 is 20 times smaller than V2. So this one's 400 times smaller when you square it. So yeah, I guess it is effectively at rest. So I was wrong when I first saw that, but it's close. So watch out for that area, right? That was one of the things that may have tripped you up, was that the area is 5 times that. There's 5 times the nozzle, or right there, 5 times pi diameter over square. Okay. All right. So here, because we had the numbers, you could just look at them, square them, and see. The idea here is this. I know I'm glossing over a bit here, but watch. We're going to stick these velocities into this equation. And when we do that, we square both of them. The idea is, if one of them is this small already, when you square it, it's even smaller. And so this term is really small. That's why we're ignoring it. Because when you plug it in and square it, it's so small it doesn't matter. All right. Where'd that go? Okay, determine the pressure in the mains. How do we do it?
Bernoulli equation.
Bernoulli equation. There it is, right? Boom, 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 boom. We said this term's negligible. If you weren't sure, you'd plug it in and discover it makes no difference. Think about it. This number is 10 to the fifth. This one is 1/2 of 1,000 times 0.01. That's so tiny. All right. And then, yeah, this term's pretty, okay, so we got it. Watch out. Bernoulli uses height, not depth. I punch in all those numbers. I set the height of the main as 0. I ignored the negligible V1. Oh, whoops. V1 was the speed at the mains. I'm sorry. V1 was the tiny one. I apologize. V1 was small. So these two terms drop out. We got this thing going. There you go. 20 PSI. Okay. Now, in this case, what's the point of this? I found out how much water pressure is needed to make this fountain run. So now you would know, if you were designing an ornamental fountain, how much water pressure you need in the main. So maybe you need to pump or compress the fluid with air and do something, right? Do whatever you got to do to get that pressure. That's a different engineering challenge. The first part is figuring out how much pressure do you need to make the effect that you want. And that's part of engineering. All right. I don't know.
Designing. Oh,
go ahead.
Oh, I think designing a water park would be cooler.
Yeah, it'd be pretty cool, right? Yeah. There's probably some information you could figure out. Like, I don't know. There's trade-offs. Sometimes it's easiest just to design by building something called a prototype and then just making it better. There's also times where you should first do some quick calculations to see if you'd be wasting your time. For example, go ahead.
Because like, what if I wanted to like figure out like how to like make a slide so no one's like slides off of it like while the water is running? Because like that'd be a disaster.
That would be bad. So what would be the issue?
I like make sure there's no friction.
The radius of curvature. That's when you lose contact, when you go over a hill. If you go down and like this, no trouble, because the normal force is large and upwards. When you go over the top of a hill, the normal force is upwards. That means your mg is the largest possible force. So people catching air is trouble. So what would you do? You would plot the shape of the track and figure out the radius of curvature at any point.
Oh, that's cool.
It's almost like you would want to do, let's see what I got here. It's almost like you could imagine making a polynomial. Whoops, let me get this thing out of the way. Imagine you took a polynomial and plotted it and pretended you made a track out of it. Right? So Trey and I did this one, right? So you draw a path, but we can go down to here and pick anything you want. Here, let me see if I can give you this. This is something Trey and I are working on for that Cal Poly crap. Where's the chat? Where's the chat? My apologies if I already showed you this, but we could do so you could draw a roller coaster like this using a polynomial or a water slide. And then you could run this thing and we could show the acceleration arrow or the velocity arrow. We could even show the turn radius. So I'm going to run this. And as this goes, I hit pause right here. The idea is you'd figure out the radius of curvature at any point on the track. And so when you're going through the bottom, you get a huge upwards acceleration, right? Here's the problem. You need a large downward acceleration to stay on the track. Agreed?
Yes.
So what's going to provide that downwards force to produce the acceleration? Only your weight. So right here, look at the required downward acceleration. It's not perfect. Let me see if I can. Oh, I went a little too fast there, but right now, which component of the acceleration is approximately equal to the downwards acceleration?
AC.
Is your weight going to hold you on this track?
Probably not.
What's the acceleration your weight can give you? About? $10. Anytime this number is greater than 10, people are going to fly off the track, right?
Yeah.
Gosh, if only there was some way you could mess around designing different shaped tracks. Oh. Hmm. But you could design, oh, this is kind of a bad one, huh? But you could mess around with this and make different size tracks and things and see what happens. Is that enough on that?
Yeah. I just think water parks are cool, and I just wanted to understand a
Yeah.
little bit.
Check this out. Even though it's messy, these are things you did in your rotation lab, AC and all this stuff. And okay, this is kind of long and ugly here, but right. This is all just stuff for the visuals. Who cares? Right? Oh my gosh, visuals. Okay, so gosh, this is complicated. Okay, yeah, so he's checked. Yeah, there's a lot involved in doing this, I guess. But here's the main part of the loop that does physics. This is the part I wrote, and then traded all the rest, all the hard stuff. But the idea here is you figure out the acceleration by saying it's the change in velocity over the change in time. Now here I made the velocity an array, but whatever, right? And then you get the component by using these dot products and hats. So these, right? So this gets you the part that's tangent to the curve. You subtract off the rest to get the part that's perpendicular to the curve. And then from that, you could figure out somewhere in here, I figured out the radius. Where did I do that? Here's how I got the radius. I know that AC equals V squared over R, and this is basically me flipping that around to solve for the radius of curvature. If AC equals V squared over R, the radius is V squared over AC. So you use that to figure out where the circle is. I know this is probably too much. Look at this. Isn't this crazy? This is a lot of stuff. It's pretty amazing that he did all that. I am so impressed. All right, let's stop there. But this is not beyond you, right? Trey didn't know how to do this 2 weeks ago. He figured it out in 2 weeks. I didn't know how to do that code 2 weeks ago. And I just said, well, what should it be? And I thought it through with physics and made it up, right? And so I had never seen it. I didn't read anything. You can do the same thing too. And yeah, Trey is really good. If you guys want to learn how to get good, here's the secret. Tutor the class you really care about. If you tutor a class, you become the expert. Trey has tutored this class 3 times now. Once with me a year ago, once with Youngblood last semester, and then once again with me. And you just become so good at it. Yeah. Students ask the weirdest stuff. You guys still ask me questions I've never thought of. Anyways, we should